Hi, my name is Nel, and I'll present a new way of thinking about learning control by a method we call iterative inversion. Humans can easily perform new control tasks in zero or just few shots. How can we train large models to perform diverse control tasks? In essence, we would like to train an agent that can master its domain by performing diverse tasks given an embeddings that describe them. The problem setting is as follows. We take a video of an expert trajectory we wish to imitate and encode it into an embedding, for example, using WikiVE. This embedding doesn't contain any explicit information about the actions taken. Our goal is to train a policy that takes as input this embedding and a history of states and takes actions that reconstruct the trajectory in the video. Ideally, we want to learn to perform any trajectory in the domain, but in practice, since the space of all possible trajectories is high-dimensional and too diverse, we only try to imitate trajectories that are in distribution with the desired expert behaviors. We use a policy with two inputs, the trajectory embedding it tries to imitate, and the current state history. We perform rollouts with this policy, embed their videos, and then train the policy using supervised learning on the rollouts and their embeddings. This algorithm is similar to goal condition supervised learning, GCSL, but instead of using the goal state, we take the entire trajectory embedding. But isn't it surprising that it works? Notice that the desired embeddings are only used for generating rollouts, but not directly during training. Essentially, this procedure only optimizes the policy to imitate trajectories induced by itself. Our main novelty is how fitting in the desired embeddings as input to the policy rollouts acts to steer the learning towards the desired trajectory distribution. Here is a model to understand this phenomenon. We want to invert a function in the array of the desired outputs, z1 star to z3 star, but we don't know the corresponding inputs. We only have inputs from a random initial policy, say x1 to x3 shown here. Essentially, what iterative inversion does is calculates the function outputs or initial inputs, find a new inverted function by regressing these input-output pairs, calculate new inputs by feeding the desired outputs to the new inverted function, then we repeat this simple process. In the paper, we show convergence of this method when using linear regression by relating it to Newton's method. To our knowledge, this is a new learning principle that works by iteratively inverting a function. It has the benefits of not using any kind of rewards. It only uses supervised learning with MSE over the action sequences. This means that we can use stable supervised learning methods for training very large models, as we do in our experiments with GPT. Our first results are with a 2D particle robot. This is a simple environment, but the intents fed the policy were high-dimensional and generated by passing the rendered videos through our WikiVE encoder. We look at two different movements, splines and move then stop. In the videos, we see the policy imitates the different movements, which are very different than those a random initial policy can induce. An interesting question we ask is whether the desired behaviors really steer the learning differently. We tried steering with splines and validating on move then stop, and vice versa, and we see that indeed steering takes the initial policy to different places. The hopper is a more challenging environment for our method, since the dynamics are more complex and hopping needs to be done exactly right at a very particular moment. Also, the initial policy keeps falling. Nevertheless, we see that our policy was able to precisely imitate the hopping behavior. To recap, we propose an algorithm for learning control based on a new idea that the input intents can steer the policy and overcome distribution shift, and we show how it theoretically relates to Newton's method. The benefit of our method is that it only uses supervised learning, so we can train very large models like transformer policies. We also showed that we are able to learn diverse behaviors on challenging domains. Thank you, and please check out our paper and website for more videos, benchmarks, and information.